Greetings. Today we're going to learn about congruence of integers. Given two integers a and b, and given a natural number n, we say that the two integers a and b are congruent modulo n, and we write it this way: a and b are congruent modulo n if n divides the difference. Now, for example, 3 is congruent to 23 mod 10 because their difference is 20, and that's a multiple of 10, and 242 and 12 are congruent mod 10 because their difference is 230. Well, one of them is negative, but the divides will take care of that. Now, one way to think about it is that when divided by 10, the remainders are the same. So here the remainders are 3, and here the remainders are 2. So you can think of modular arithmetic as looking at remainders. A very common example is clock arithmetic. When you add 5 hours to 8 o'clock, then you get 1 o'clock. So you wrap around mod 12. Now, looking at remainders is a very convenient way of thinking about congruence. So here is a theorem that says we can actually do that. So this is the same setup, and a is congruent b mod n if and only if a and b have the same remainder when divided by n. This is not what the definition says. The definition says that n divides the difference, but this following theorem is something we can prove, and that is an easy way, a nice way of thinking what modular arithmetic means. One of the things we can do with modular arithmetic is that we can add things that are congruent. For example, if we add these two things, we get 245 and we get 35. And those are congruent mod 10. Now, if we have things that are congruent and we have things congruent and we add them, they're still congruent. And you can almost see this happening. Yeah, the difference is a multiple of 10 here. The difference is a multiple of 10 here. So when you add them, the difference is still a multiple of 10. But that's something we would like a proof of. So here goes, and here is a proof. So look at that example again. Here is a theorem that says if we have 4 numbers and 2 of them are congruent, a and b are congruent mod n, and c and d are congruent mod n, then a plus c and b plus d are congruent mod n. Now let's go ahead and prove this. I would encourage you to pause this video and think about how you would approach it, and then resume the video whenever you have figured out something that you would do, and then keep pausing and resuming as you can to have the maximum benefit of trying things yourself. As usual, when we are writing proofs, we say some upfront assumptions, and then we can now start on one side. So we can suppose that a is congruent to b mod n. When you're saying a congruent to b mod n, it's polite to pause after a congruent to b. So a is congruent to b mod n, and c is congruent to d mod n. Well, that's the cadence of which we would usually read these symbols. So then what would you do? Again, pause and think about it. Essentially, we'll want to use the one definition we have. Yeah? By definition of congruence, we have, let's bring back the definition. The definition says that n divides the difference. So n divides a minus b, and n divides c minus d. And we just keep pushing it through. Yeah, by definition of divides, we can write this out. By definition of divides, I suppose we should write something like we have, if n divides a minus b, then that means a minus b is equal to n times something. That's an integer. Let's say x. For some integer x, and c minus d is some integer multiple of n. Then since we're trying to prove that a plus c is congruent to b plus d, if we look ahead, we know that we would like to calculate the left side minus the right side, let's say. So then a plus c minus b plus d is equal to, and we can rearrange this, a minus b plus c minus d. Now, no one in their right mind would be writing these things without reason. Yeah, but we know, looking ahead, that we want to calculate a plus c minus b plus d, the left side of the congruence minus the right side of the congruence. It doesn't matter if it's left or right, but just one side minus the other side. And we also know that we already have defined a minus b and c minus d, so we want to leverage that. That's why we're rewriting. So we're always looking ahead and behind and trying to figure out how to get to where we want. So nx minus ny, and we can factor that. Oh, is this plus nx plus ny? So n times x plus y. And you could give a new variable the value of x plus y and say n. Now that's a multiple of n. But or you could simply say that in the next line, as x plus y is an integer, and it's very important that it's an integer. So we really want to emphasize that part, perhaps explaining that this is by the closure property, by closure. So by definition of congruent, I suppose one more step. So by definition of divisible, divides, we get that n divides a plus c minus b plus d, and then we can unroll this one more time. So a plus c is congruent to b plus d mod n, by definition of congruence. And we're done. So that traces out through careful definition that the difference between the two sides, and then when we add them, we get, it's still a multiple of n, of course. But this careful proof gives substantiates the intuition that we had. Now let's come back to this theorem that we mentioned, that if a and b are a congruent modulo n, then they have the same remainder when divided by n, and vice versa. This is an if and only if characterization. In order to know what remainder means, of course you know that from kindergarten, but let's also think about the division algorithm. If we have two integers, and b is greater than 0, so we're not trying to divide by 0, there exists a unique q and r. Well, there exists a unique q and r, and these are integers, so that a is equal to qb plus r. Think of q as quotient and r as remainder. So if you divide a by b, you get the quotient is q and the remainder is r. And we stipulate that the remainder should be between 0 and b. It could be 0 if it evenly divides. It could be as big as slightly below b. If it reaches b, the remainder, then you should actually divide through and get one more in the quotient. Right? So this is a fact that you probably know from childhood when you're learning division in kindergarten. But now we know that as a fact that we can use. And so if we come back here to think about the remainder, it simply means that if we write a in this form, so here it's not b anymore, we're dividing by n, so this would be n, and then we get certain remainder. Now let's prove this theorem. Let's prove it in one direction. I'll leave the other direction for you to do. So proof going from right to left. So let's suppose that A and B have the same remainder. So let A and B be integers, and it's a natural number. Same setup we've been using for a while now. Let's suppose that A is equal to, let's say, xn plus r for some x and r, these are integers, and b equals yn plus r. So the key point I'm trying to make is that when divided using the division algorithm, we get when a is divided by n, we get a quotient and a remainder. I'm naming the quotients x and y, and the remainder should be the same because that's what it's saying right now. A and b have the same remainder when divided by n. So here we have these things for some y and z. So it's the same r. Okay. Well, let's subtract them. Yeah. Then a minus b is equal to xn plus r minus yn plus r. The r's cancel, and we get n times x minus y. And so that means, using the same reasoning as above, we could get that. So n divides x minus y. Sorry, that's not what I'm trying to write. Whoops. So n divides a minus b, and thus a is congruent to b mod n. I should probably cite the definitions right now, but we just did that on the previous theorem, so I'll leave that off. So that gives us what we wanted. So what we have just shown is that we can think of congruence as calculating the remainders when we divide by n and then seeing if they're the same or not. And to remind you, we also proved that if they have the same remainders, or if they are congruent, then you can add them and you will still they will still be congruent, or that you'll get the same remainders on the two sides. I would encourage you to also go and prove that with the same setup, you can show that a times c is congruent to b times d. So not only can you add congruent numbers, you can also multiply congruent numbers, and they will still be congruent. So that's it for now. Bye.